Go ahead.
Hello. So first, I would like to say I'm sorry because I was late because it was really out of my power to be on time. So today I'm going to present you something like energy-aware parallelization of real-time tasks, and I will try to call it if it's better to go sequential or parallel. So basically, this work I have done it when I was at the beginning of my PhD under the supervision of Giuseppe Paris. Now I'm a postdoc at University in Modena in hyperflat. So basically, the main focus of my talk will be on time energy models and how, based on real benchmarking, how to model energy time scaling with based on frequency changing and energy models. And I will say highlight how to do the analysis based on that models and what how to choose either execute a task in sequential way or in parallel way. And after I talk about the generalization of this model. So let's imagine that we have three threads to allocate, which are recurrent threads. So here is the thread arrival, the upper row, and down the row is the deadline of the thread, and we have three tasks which are allocated on two cores. So the first and the second tasks are allocated in the yellow core, and task 2 is allocated on the blue. So basically, the system is infeasible, and if you are going to take 2 units of time of the third task and to allocate it on blue core, so it will help us to achieve a higher schedulability bounds. So we can use parallelization to achieve higher utilization of the platform. And also, when we are parallelizing, we have a larger slack time. For example, this task which can run into 3 threads, if the 3 threads are allocated on the same core, we have less slack time than when it's used in parallel. So when we say that we have more slack time, so we can reduce the speed of the core, which is C, on the maximum speed, until reaching some limit of in terms of analysis. So in this work, which I will present, is how to select the frequency and when it is better to go sequential or parallel. So we have the real-time constraint to respect and the energy consumption, and this talk I will say how frequency, time, and energy interfere with each other, and how to do from analysis go to the implementation, and I will present a very small IPI developed by master students that I was at. So to build the energy and task model, we have run a benchmark on the Odroid XU3. So as you may know, the Odroid XU3 have 2 clusters of cores, 4 ARM Cortex A15 and 4 ARM Cortex A7, and we have an energy and power sensor on each core cluster on the memory, and we plug it all that into a power meter. So we have modified the ME bench. We instrumented the code of ME bench with real-time priorities using ChatGPT. Each task was run for 1,000 times. And this is the list of the application, the tasks we run. Basically, we try to diversify as much as possible the test applications. And basically, we modify the input data size, the task affinity, so each time we allocate tasks into different cores. And we change the core frequency and state. So we turn off some cores and turn on some others. And we measure the execution time, the power consumption of each group, and the total power. And so the benchmark that I modified is available on these websites. So in the first experiment, we allocated 1 thread on 1 little core, and we just measured the execution time. As you may see, the execution time of the task may vary as a function of the frequency, so all tasks doesn't have the same behavior when we change the frequency. So we do some nonlinear regression on these points, and more or less all the points gave us the same thing, which is that the execution time is a function, semi-linear function of the operating frequency, which we have the first constant on the ratio of a constant on the operating frequency added to another constant. So we said that the constant 2 is mainly the memory access. So to verify that, we change the input stage of data of all the tasks, and this is just for the matrix multiplication. So the results were more or less the same. As you may see, here it's not even a linear regression. We just computed const2 on different input stages of data, and it was linear. So we said, okay, const2 is for certainly highly related to the memory access. Yeah, and after we repeated more or less the same experiments, but with measuring the power consumption, and once again, the power consumption depends highly on the task that you are executing. For example, this task, FFT here, which was consuming hugely less than this case, for example. So after we did the same experiments, that here we allocate one task into one core, and two tasks onto two cores. Of course, it's the same task, and three tasks on three cores of the same type. So as you may see here, that difference between the value of this point is not 2 times the value of this, and this point is not 3 times the value of this point. So basically, when we are executing more threads of the same task, we are not duplicating the power consumption, which is in the most, more or less, most real-time works, they assume that when they allocate a task, they just have a function that is multiplied by 2, which is not totally correct. So when applied third regression, the regression was more or less satisfactory, and the problem here is how to model the execution of 2 threads, knowing the execution, the power consumption of 1 thread. So this is the main idea, the basic idea that I will try to apply in the next slides. Also, we measured the energy consumption, the power consumption of the memory. So we have just changed the frequency to see whatever, if it is really related to the memory access for a given task. And of course, we have seen that little cores consume a little bit power on the memory than the big cores, because they had little cores had less cache, so they did more access to the main memory. So later, we have computed the energy consumption, and this is the real values, DS, as always, the regression. So as you may know also, that there is, starting from the lowest frequency when we execute the task, we are losing energy, and starting from some point which we call effective frequency, we start, each frequency raising is equivalent to, each frequency raising is equivalent to an energy increase. However, this is also dependent on the task. So we cannot just say, okay, I will have a set of tasks, I want to execute them. What frequency I have to select? What is the best frequency I have to select, knowing that each task have a different effective frequency. So what we had to remember from this benchmarking is that power dissipation depends on the core type, on the operating frequency, and the task itself. And that 2 threads of the same task dissipates the same power, but not the same energy, probably. And the static energy depends on the voltage, which depends on the frequency. So we cannot just say, okay, as the real-time works, okay, the static energy is constant. Let's just do a constant alpha, which we multiply by the high-power period to compute the total energy dissipation. So the memory energy consumption is really important, and it needs to be taken into account. And when we want to set the frequency, we need to take account that the effective frequency is different for each task.
Sorry, static energy depends on the frequency. Is this obvious? Because me, I would have just said that the energy dissipated when the frequency is 0 and the processor is not running instructions. So I would say it's a constant number, but you're saying it's not.
So it's not when you are running a task.
Yeah.
So when you are doing nothing, yes, maybe it's a constant. But when you are running a task, it raises because you are running something on different CPU components, which may be activated when you are executing some or other instruction.
Yeah, but I remember the formula I read on the electronic textbook, and the power I consume while I'm doing stuff is the sum of two terms, one of which is constant.
Yeah, what is not true.
Okay.
This is what I'm saying.
Okay, that's interesting.
Okay. So let's assume that this is the more or less the platform that my students developed, my master students. We have some code and you instrument it like this. So for example, here is the main thread that you can parallelize into two threads. And in another file, you can specify all the real-time constraints, like period, deadline, and the worst execution time of each real-time section you need to execute. So by analyzing the second file, we have to build, we have to take the inputs, which are the deadline, the period, and the execution time for each thread, the parallelization input, which are the finest thread, finest parallelization granularity, and the energy coefficients for each parallel section. And we need to define the allocation of each thread to each core, and either the task will execute in sequential or in parallel. And of course, we need to select the operating frequency for each core group and the core state. So based on the text file that was described as input, we build the task model. So either the task can execute in sequential with a certain execution time amount. And you can imagine that it may have several ways to be parallelized. So here it's parallelized to 2 threads, and here it's parallelized to 4 threads. The goal of the analysis is to define which are the threads that need to be allocated on the same core, or we are going to run each thread on different core, or how the task is going to be executed. So we call each point here the cut point. So it's just a name that we have chosen to give. And the sum of the execution of all the threads should be greater than the sequential execution, which is obvious. And for each get point, we have a set of coefficients to compute the energy consumption of that thread. So the basic idea of the analysis is to say, okay, what is the maximum execution time that I can allocate for a given task into a given core? So first, I start by saying, okay, let's, for example, here this example, in which we have 2 threads that are allocated on the same core, and we have this task, and we want to allocate it on the same core. So the basic idea is to say, okay, I will try to allocate the sequential version. So I will allocate all the threads into the same core. So, and simply because when executing the sequential version, we don't have parallelization overheads. So if we execute this task, the system will not be feasible. So we try to reduce the execution time of the sequential version each time and verify feasibility. And when we find the feasible system, we say, okay, now this is the maximum execution time that I can allocate on this core. However, it's not done by an incremental way like this. It's more smart, so it defines directly the maximum amount of the execution time that we have to allocate. And here, of course, as it's 4, so the execution time, so we cannot allocate the sequential execution. However, we can allocate this thread on the current core or 2 of this thread on the current core. So we in this example, for example, we keep that solution, this thread point, because it allows more flexibility in allocation in the future. So if we are going to allocate this thread, so we don't have flexibility to allocate that task on 2 different cores. So the basic idea is just the best fit algorithm. So each time I select a task and the core, and I try to allocate tasks in sequential first. If I cannot, I try to define the maximum execution time that I can allocate on the task, and allocate all the threads that have execution time less on that core and the others on future iteration. So if you want more details, you can just refer to the papers. And here is exactly the model that I'm presenting. And here is an extension for really the DAG-based tasks. So all the models which are modeled by OpenMP related, let's say the same way as OpenMP. So more or less, we have this. I come back to the same example, and the platform that was developed by my students. So it states that it do the analysis, and after, if, for example, for some of the analysis say that the first thread will be allocated here and the second thread will be allocated here, it will generate two different threads. It will generate all the source code needed to execute it, and it defines the affinity and whatever is needed. So the basic idea is to generate source code so that the user can modify it later. And if, for example, the two threads have to be allocated on the same core, the source code are merged and in one thread. Also, we generate the main function using shed deadline. So let's now talk about this is the allocation. Now let's say how to select the frequency. Of course, to do the analysis, we need at each time to know the execution time of the task. And so basically, the most stupid way to do it is to analyze from the lowest frequency to the highest frequency, which may make the analysis too much complex. So we need to reduce the analysis, execute the analysis time. So first, I define the computation strength as the operating frequency, or the ratio between the operating frequency and the maximum frequency, and ND, which is the number of active cores. So the optimal frequency is somewhere there in the interval from the minimum to the maximum. But we have the effective frequency, the minimum effective frequency, which is here. So it can reduce the already reduced execution, the reserve space of the optimal frequency. So the optimal frequency is somewhere there. And we have also the maximum utilization and the maximum strength that can be given by a task. So utilization is the ratio between the execution time of each thread, the sum of the execution time of each thread, depending on, of course, on the operating frequency, on the task period. So the needed strength here, computation strength, the needed computation strength to a task system to be feasible is somewhere here, right? Because we cannot schedule more than utilization that we have. So based on that, we can compute the minimum bound of the optimal frequency based on the number of cores and the maximum utilization. It will reduce more reserve space. So later, when we are going to do the analysis, we just need to check this reduced interval. So basically, if the maximum utilization is greater on the number of cores in a given core group, so all the cores of a given core group or core cluster will be set to the maximum operating frequency, and we start to allocate tasks onto more capacity core types. So in this big.LITTLE configuration, so we start by allocating all the threads on little cores, and after when we reach the maximum frequency on little cores, we start allocating threads onto big cores. So the platform developed by my students allows to synchronize with a lot of options, like synchronizing threads at different core wake up, using shed deadline, and may select a lot of options on code generation, like allow task migration and stuff like this. Allow variable sharing, but it's under developing to take it into account into analysis. So in the second paper that I presented earlier, we did synchronization while sharing variables, but platform as it is now doesn't take that into account. So, and we do something like a pragma parallel for OpenMP for independent iteration for loops. So we generate all the source code in an automatic manner. So to conclude, the parallelization can help us to achieve a better feasibility and energy efficiency. So it's better always to go sequential when it is possible. And sometimes when the frequency, the select frequency is very low, maybe it's better to pack some tasks and turn off more cores. So the thing that I'm not taking into account, so it's the analysis. So when I select the frequency, everything is done offline before executing the system. So when the task ends its execution before the worst its worst execution time and reserve budget, what are we going to do? So basically, we are thinking about doing something like sleep task scheduling, and it's still an open question because I started a new work at Modena, and I'm working on new topics. That's it.
So did you understand if you actually run tests on the platform? I mean, this is a feasibility analysis, right?
Yes.
On this set of tests.
Yes.
You actually have data of running your. So you generate code. You
Yes.
actually have data showing how it performs on the platform you use for.
So basically, this the platform that generates the source code was done by master students, and unfortunately, it's for just 3 months, 3 or 4 months, and we were not able to really test the performances and the respects of the deadlines using that. So, but the basic idea was not about really testing or do a final platform, but just to help the user to generate parallel tasks, and so he doesn't have to care about where to execute this task or that task. And so the basic idea is this is why we generate source code so he can more or less modify it later.
Any other question?
Yes?
I saw that you figured that the static and it is kind of frequency. Have you considered the inverse?
No, not at all. So this is another work which we are working with the University of Valenciennes.
Okay.
We are working on the thermal aware scheduling, and it's still like project still is at the beginning.
Yeah, I mean, of course, that you are already working on it. So you don't consider the temperature, you might end up with a thermal runaway.
Yes, exactly. So this is why we are trying to work now on thermal aware scheduling.
Okay.
Okay.
Thank you.
Thank you.